Okay. We start the second talk will be given by Sergei Nazarenko, and he will talk about superfluid turbulence in classical quantum and crossover regions.
Thank you. Okay, so let me, you saw a list of collaborators about which we already decided that they are not from the same paper. But, recently, I guess I most intensely worked with Viktor Lvov, Alexei Rudenko, and Gillian Arato. So let me just tell you about superfluid turbulence briefly. Some pretty elementary facts first of all. That what it is, as an object. Superfluid turbulence at temperatures close to zero, when normal component is negligible, consists of a selection, you can say spaghetti or tangle of quantized vortex filaments. So each vortex filament has a quantum of circulation, which is Planck's constant divided by mass of an atom. If it's helium-4, it's mass of helium-4 atom. And so these filaments have thickness close to atomic size, so very thin, almost singular. And the models for them, one of the most popular models is a Biot-Savart equation, which is a reduction of earlier equation, when we formulate it in an integral way. But of course, in such, so where R denotes a line, vortex line, and it depends on parameter S and time. Okay, and so each element of vortex line is moved by velocity field induced by all the rest of elements on the same line and on the other lines. But this kind of reduction is opposed, because you can see, of course, when R tends to S, it's a divergent integral. And so the kind of phenomenological way to fix that is to say that to take into account the vortex core radius and say, well, all that is integrated with R minus S greater than a certain constant, which we call vortex radius. And so numerical methods for computing that were initiated by Klaus Schwarz, who basically computed this kind of equation, maybe even simpler version with local induction approximation, complemented with a way that vortices can cross each other. They reconnect. When they approach each other, then they will reconnect. So what's the vortex reconnection? So suppose you have this configuration, and then you should allow for it to go into that one. And this is allowed, this is not allowed by Killian theorem in classical fluids, but it's allowed in superfluids, because apparently the difference between the classical motion and quantum are very close. There appears term so-called quantum pressure that allows you to avoid this constraint of Killian circulation theorem. And so within Biot-Savart equation it's not included, but it's phenomenologically implemented in numerics when two vortex lines get close to a distance, comparable to this cutoff radius A. You just simply reconnect the filaments. When that happens. So another very popular model of superfluid turbulence is a Gross-Petaevsky equation. So it's a Schrödinger equation with a nonlinear term, nonlinear Schrödinger equation. And nonlinear objects, it's known as defocusing case, or so it corresponds to the repulsive potential if we're talking about dilute gases. So, here's, I show sort of example of numerical simulation in 3D when one forces it in the same way as one would force in Navier-Stokes turbulence, namely you force somewhere at low wave numbers and you produce cascade, right? But what's interesting, what's happening, kind of striking, in this case, when you wait long enough, when you see what happens instead of homogeneous isotropic field, right? This is physical space.
You continue forcing all the time?
That's continuum, forcing is continued, yes. And that's, you see, out of that disorder, you get again these worms or lines or spaghetti.
This color is all quantized vortices. There is white, there is...
This color is levels, is the kind of contours of motor size squared, taken at some low value of psi.
So it's where psi close to zero.
You mark the regions where psi close to zero, and you see that that you actually get more and more order, and these vortices which are defects of the phase of psi sort of become large scale, and eventually large scale order appears, so they become more and more large scale. So now the kind of pretty well accepted picture of what's happening, although not necessarily a correct one, that at large scales quantum turbulence looks like, superfluid turbulence looks like usual classical Kolmogorov turbulence, with eddies cascading like in the Richardson picture, and Kolmogorov spectrum forming. So by large scales, I mean the scales which are greater than separation, mean separation of the nearby vortex lines, the spaghetti. So if you take these eddies of size like this, so then they're made from average of many spaghettis, and basically you kind of coarse grain this large eddy does not feel the discretization effects, and the picture is that at the end, the equations are the same as the usual Navier-Stokes at these scales, and so dynamics have to be the same, and turbulence has to look the same. So, however, I mean, there is of course a difference. It's not Navier-Stokes, there is no viscosity, right? So inevitably then this cascade will proceed to the scale L, the mean separation. And the question will arise, what happens then after that, what happens with the energy cascade. So it's a superfluid turbulence. For me, it's an extremely fascinating object, where you move from laws of classical physics to quantum gradually, along the cascade, and there is a crossover region which is the most exciting and probably least understood one. And I'm quite excited to to learn more what's happening in this case. So viscous dissipation, that applies only for classical fluids. But now we have to ask what happens in quantum case.
You said larger there, scales larger, do you mean smaller? Same picture for superfluid turbulence at scales?
Larger than intervortex separation, right? So you at the scale is larger, right? So like on the first slide, you saw it's vortex tangle, but it's not just random spaghetti, they're kind of polarized. So when you take a large scale, this average vorticity is not zero normally. It's like a vortex bundle, right? but but because the scale is so much bigger than each constituent discrete vortex, you could assume that actually, it's almost like a continuous limit. So at scale L, when energy reaches those scales, you could expect reconnections, and indeed in numerical simulations they do happen. I mean, what I showed here. I mean, the great, here again, I just plot two level sets of mod psi squared, right, for two filaments approaching each other and reconnecting. In fact, the reconnections well studied in the context of fluid dynamics, right, and MHD. I mean, great difference in gross-Petaevsky and superfluids, that they are much milder. They are not so vicious as in earlier equations. Because you can think of gross-Petaevsky as a regularized version of Euler. You don't have singularity at all when reconnection happens. There is no question about that. Okay, so it happens smoothly. Instead of some sharp gradients with infinite vorticity, you actually cross point where psi is zero. Vortexes where psi is zero. Vortex is hollow. There's nothing inside vortex. It's zero density, right? And so when it crosses it very smoothly, when psi close to zero, dynamics actually is almost linear, because nonlinear term in gross-Petaevsky is very small, at small psi. And in fact, what's shown here is analytical solution for vortex reconnection. If you notice that at the reconnection point nonlinearity is zero, then you can expand the small nonlinearity in the small vicinity of reconnection in space and time, and construct solution as series, analytical solution, as convergent series, and then plot them, and that's what you get. So now, once you cross this, this is at scale L, and the connections will, when they just happen, they produce sharp corners like that, right? And the sharp corners will relax. If you imagine this is kind of a rubber strings or something, they will relax and they will produce waves propagating along them. Okay. And this is illustrated here. So we started with a regular configuration of some, vortices like Taylor-Green kind of configuration. And then they quickly reconnect, and you see these vortex filaments, and there are some waves traveling on background of them. And so this is now believed that this is precisely these waves. When they interact nonlinear with each other, they carry energy further to smaller scales. So these waves propagating on vortex filaments transfer their energy to even shorter waves, and shorter waves, and shorter waves, until they reach such short waves which radiate acoustic energy. They radiate phonons, and this is the mechanism of dissipation into heat. So, so this is pretty much was, if not generally accepted picture, at least widely accepted picture. But of course, there are big battles which are ongoing about the details, about what exactly happens, and how. How to describe these mechanisms. So here's a theory of Kelvin wave turbulence that was originally formulated and put forward by Kozik and Svistunov in the framework of wave turbulence. So essentially, they start with Biot-Savart equation. Write it in Fourier space. Okay, they write it for configuration for a function, which is essentially they introduce, let's say, vortex filament this is z-axis. And the parameterized vortex filament as function x, x as function of z and t plus I, y, z and t, and let's call it function w, right? Complex variables, which is depending on one physical space dimension and time. And Fourier transform of that is AK, and this is a Hamiltonian system. And if you write Hamiltonian is pretty horrible, and actually the correct version of it was only obtained recently in my paper with Victor Lvov, Alexei Rudenko, and Jason Lowry. But in spite of all that, I mean, scaling properties of this coefficient are much easier to understand and obtain, and they were realized by Kozik and Svistanov. And based on them, they derived a scaling solution for, well, first of all, they wrote a closure equation for the spectrum of this quantity of scaling wave amplitudes. Okay, wave action spectrum. So this is the wave kinetic equation, which describes a 6-wave process, 3-wave merging to give rise to other 3 waves. So kind of 3-to-3 collision with conservation of energy and momentum. So this delta simply shorthand for delta similar delta function, but for wave numbers. So now the
Why 6 waves?
why 6 waves?
Yeah.
That's a very good question. This is because to main approximation, right? So the dispersion relation for waves is like this. Okay, and it's not well. First of all, you have you want symmetry for in the equation, so all the processes have to be odd order. It cannot be a 3-wave process or 5-wave. So it will have to be either 4-wave or further, right? So 4-wave processes 2-to-2 are forbidden. You cannot solve the resonant condition for 4 waves with a function like that. In fact, for any k to alpha with alpha greater than 0, when dimension is 1, 4-wave interactions are absent because resonant conditions can be satisfied. So, the 6-wave is the leading process. Appears. Okay, so now, so in line with a general sort of framework of wave turbulence, which is just like unusual turbulence picture. Energy is injected at small wave number, dissipated at some high wave number, and gradually cascades scale by scale through the inertial range. Okay, one can derive solutions of so-called Kolmogorov-Zakharov type, which were originally discovered in wave turbulence context by Zakharov in his 65 paper and his PhD thesis. And so application of these ideas, one can obtain scaling for that spectra just solely based on scaling of interaction coefficient, dispersion relation, so just using dimensional analysis. And this was done by Kozik and Svistanov, and they obtained this spectrum. -7/5. So now, if you try to put together all these ingredients, what was sort of what people did is the following. Okay, so you have Kolmogorov -5/3 hydrodynamic spectrum at large scales, at low wave numbers, and then you have minus 7/5 spectrum there. And then, of course, you have to do something, you know, compare it with something, right? But the thing is, experimentally, you can't access scales of Kelvin waves. They're very tiny. You have to be anemometers of micron size. I mean, maybe in principle they're possible, but not yet. You know, not been done yet. So one then has to sort of see what are the consequences for sort of global properties of the system of this picture. And one of the predictions that was sort of argued in this paper of Stalk et al. Is that if picture looks like that, then what they measure is dissipation of the total vortex line length. What rate it dissipates. And the law of this dissipation leads to concept of so-called effective viscosity. So they say it will dissipate as if it was just Navier-Stokes turbulence with viscosity like this. And from this picture, if you just match these two spectra, you invoke that effective viscosity is just of order of the quantum of circulation. And if you think a little bit about that, there can't be anything else, because it's the only dimensional quantity available to you in that system. Quantum of circulation, right? So it has to be up to a coefficient of order 1, of course. So, but then, you know, came Victor and, you know, told me, you know, oh look, you know, what do you think? You know, we can't really match these two spectra smoothly at L, at scale L. Why? Because the prefactors are totally fixed in Kolmogorov spectrum and in Kelvin wave spectrum. So there has to be jump. And if you think about it a little bit, then it's quite natural. I mean, that there should be no smooth transition from one to another. Because, you know, in Kolmogorov turbulence sets eddies they interact, and the rate of interaction is efficient and fast and strong turbulence. Whereas when you come to wave turbulence range, it's much more sluggish wave interactions, and so you expect stagnation of the energy spectrum, a bottleneck.
So this plot that you have here is a schematic? Or
it's absolutely schematic, yes. So, and then, so we came up with this picture of bottleneck. That is one of the current controversies, whether it exists or not. But so basically, it's again, it's thermalization. You don't expect, of course, a jump. You expect instead the thermalized part of the spectrum, which is a little bit leaking its energy toward Kelvin waves. But it develops such bulge. And so, I mean, which if you use, I mean, the most simple closure for turbulence, so-called Leith model, you can even analytically write expression for this kind of spectrum that transitions from -5 to a squared. And of course, I mean, the work, the numerical work.
There is no genuine viscosity. I mean, in there, nothing that would lead to the solution falling off exponentially or so. Right?
Absolutely, yes. So I mean, in this model, all exponential decays, I simply shut down.
No, I don't mean the Leith model, the physical model.
Physical model, you mean in DSLR?
Gross-Pitaevsky.
In Gross-Pitaevsky exponential follow-ups. Okay, so we don't know, but I mean further down we expect phonon radiation.
No, I mean I'm just applying whose principle was it, Chomredis or so, but if you seem to be discovering something nice, I give you hell.
Yeah.
Heisenberg also had a weird equation, which was giving us k minus 7. And then it had the high k when it ought to be an exponential, as pointed out. So I wonder if with the Leith equation they correctly describe certain things and very badly others. So I wonder
It's possible,
if
I
these
mean-
algebraic fall-off at high k is genuine or not.
At
I'm not
high
questioning
k,
the
at high
ordinary
k, it
type.
doesn't algebraically
I'm
fall off.
questioning
It
the
goes to k
functional
squared.
form of how it decreases beyond it.
Or beyond it.
Yeah,
I mean, it's,
yeah.
it's okay. So the lift model I was mentioning only for this region. Okay. But for this, you can write similar differential approximations, whatever. So let's, that's the whole,
Mm-hmm.
it's best to.
Where are the phonons and the rotons in this picture? Since you're
There's no rotons, but the phonons are further somewhere. Way out there, yeah. So they will be radiated by Kelvin waves eventually. So next slide. Okay, so effective viscosity. But essentially, what's nice about picture like this, although it's schematic, I mean it gives you sort of a prediction, quantitative prediction for a reduction of a great reduction of effective viscosity by a big factor of lambda minus 5, where lambda is the log of L to A, to vortex radius. It's usually of order 10, this factor lambda. So, and to his power, it's a great factor. And so, indeed, after that was a series of experiments that actually compiled, in different experiments, but they compiled on the same graph in paper of Golov and collaborators. And we see if effective viscosity changes from something of order 1 when temperature, when normal component was present, but it greatly reduces several orders magnitude when you go to pure superfluid regime. So it's kind of indirect sort of.
I mean, but that's been known for a long time. So what's new about this? I mean, at least the temperature dependence of the viscosity below the landing point.
It's not viscosity; it's effective viscosity. It's the rate of dissipation of the total length of superfluid of vortices. So that's the effective viscosity thing that okay, so I can't go into detail now to describe what it precisely is. It's as you say, okay, from the picture of the spectrum, you have some sort of prediction for the rate of dissipation of the energy, how the total global time will decay. And so concept of effective viscosity is to say, well, it behaves with the same kind of power law, T2 minus 3 halves, as if it was Kolmogorov, if viscosity was like this. Okay, and so for usual prediction was like this, quantum of circulation, but I mean this bottleneck feature reduces it considerably.
But what do they measure exactly? Because in Kolmogorov theory, only the dissipation wave number is depending on the viscosity. The macroscopic thing, like energy dissipation, is independent of viscosity. So what
No, but I mean the rate at which the total energy of the turbulence is decaying will be
No, that the energy dissipation in Kolmogorov theory is not dependent on viscosity.
It's okay. It's not exactly energy; it's entropy.
Okay, so they measure the vortex density
Yeah.
and how it decays. Okay.
Yeah. So anyway, my time is, I guess, running up soon. Okay, so I should really tell some interesting stuff here. So it turns out actually that first of all, that's all great for 6-wave wave turbulence based on 6-wave process. But it is known, that these spectra, this wave turbulence KZ type spectra, are only relevant if they are local. Locality is assumed in derivation. From dimensional analysis, you can't check locality, but you can, of course, do it, doing hard work and checking converse collision integral. And after we've done that, we discovered it's non-local. So. And non-local means there is no mathematical solution like that, it's irrelevant. And it's non-local because this collision integral diverges at small wave numbers, infrared divergence, and in a peculiar way. So it diverges when 2 out of 6 wave numbers tend to 0. And from that you can make an assumption that the true theory will have to be non-local in such a way that 2 of the wave numbers should be taken near the cutoff and the other 3 in the inertial range. And so you then, out of 6 wave kinetic equation, you get effective 1, 2, 3, 4 wave kinetic equation, as written here. And good news that in addition to, okay, so a reduction of order of the process, the interaction coefficient, which is absolutely horrible, contains 20,000 terms for 6 wave. But it reduces to just a product of 4 wave numbers when you take limit and when at least one of the wave numbers tends to 0. So asymptotically it's a absolutely simple expression, and so it's becoming a nice and beautiful model. And it has a solution of KZ type, now local, as it turns out. You can check and see that it's now local within this 4-wave kinetic equation. An exponent, quite surprisingly, but probably completely accidentally, -5/3.
So do you still have a bottleneck with that or not?
Yes, and the bottleneck, yes, and the amount of bottleneck seems to be the same.
Has anybody seen this in numerical studies?
And I'm coming to that. Okay, so, well, first of all, let me say one step back for a second from the kinetic equation. So I have this asymptotic form now for interaction coefficient, and I say, why not to write dynamic equation that would effective dynamic equation with this interaction coefficient, and I'll get this model, which we call local nonlinear equation. Okay, so this kind of equation and corresponds to this Hamiltonian, which we can put through computer and get spectrum like that. So forcing here, this is compensated. This is cos existence of exponent. This is this the new exponent 5/3, right? And it turns out that the spectrum, not only exponent seem to agree, we compensate the spectrum, right? But also the prefactors. And I want to emphasize in wave turbulence, it's probably the very first example when prefactor is computed and it coincides with prediction of the theory. So even in the most classical water wave systems, it's never been like that. I mean, the prefactor constant, Kolmogorov-Zakharov constant, is always off by at least an order of magnitude. So we were quite amazed to see that. So, yes, whether it can be observed or not. I mean, a lot of people reported observation -5/3 spectrum in gross-Petaevsky simulations, starting with Nora and Barashe paper, where it was very for good reason said that it's like Kolmogorov, because they were actually dealing with scales which are greater than L intervortex separation, and that's consistent with the picture I painted before. But further authors actually observed -5/3 in the scales which were below L, and that's puzzling. Okay, and also in our recent simulation, a picture which I showed to you, and this is a picture from that simulation of David Roman and Miguel narrated my paper with them together.
This is a simulation of what?
3D Navier-Stokes, 3D Gross-Petaevsky, forced at low wave numbers, right, and dissipated at high wave numbers with higher viscosity, right? So you then wait and wait, and you see, remember, we'll wait long enough, you have this vortex, large-scale vortices up here. If you wait very long time, you actually see only one single vortex left, and it goes around and kind of wobbles and have killing waves on it. Okay?
It's the same size as a forcing. Forcing is the same scale.
As this round vortex in the end. Is that so?
Yes. Yeah. So the scale of the
But how
portion
do you
is
force?
almost the biggest scale of the system. This actually the box is it's not a computational box, it's a zoom.
And how do you force? Sorry?
Forcing the usual forcing, I think they just add each time something random, you know, you put random in the system, some Fourier, you know, right hand side with some random phase, you know, at some wave numbers, at low wave number. And in a ring,
Higher or
in a
not?
ring, in a ring,
Ah, they force in the ring.
in a ring, yes. So they did
No, no, sir.
they did in many ways. I mean, it's actually very important to say what's inside the ring. Because inside the ring, if you don't dissipate, you won't see condensation. I mean, if you don't want to condensate, okay, you have to dissipate in a quite nice way inside the ring. But in this simulation,
What do you
no,
mean inside the ring? The ring was in front?
the ring in Fourier space.
There is
So-
two rings, one in physical and in Fourier, and there's not nothing.
So
But
you
why are rings in Fourier space?
Yeah.
Ring means shell.
Yeah, shell.
Shell.
But why?
But why dissipation inside this shell?
No, that I don't understand.
because there is
But I'm
inverse
thinking force.
condensation property going on, right? In inverse cascade.
If you have an inverse cascade, yes, you have to remove some energy. Otherwise you have a high law.
So in this simulation, it's not done. I mean, it's we don't dissipate. We allow condensate. That's the point.
But why
So
do
you
you have
don't-
such a large compressible energy?
Yes, and we have large compressible energy. So we separate compressible and incompressible energies, right? And we see that actually here's 5/3 for reference, right? But we see that, I mean, there is no, and it's in the range of scales. Okay, so you see there is no vortices, there is no reaches and cascade, there is no vortex bundles or anything. So there is only one single vortex ring, and it's 5/3. So our tentative hypothesis that that must be related to this spectrum of Kelvin waves going around that. And moreover, these authors that I mentioned, Subota and Gepes, you know, I think they are observing the same thing. Now, about compressible energy. Compressible energy, actually, if you put a line here, okay, so line with slope 1/2 would be Zakharov-Sagdeev spectrum of acoustic turbulence. And that's a possibility. And another clear kind of evidence of this acoustic turbulence that it's waves interacting on one line, collinear waves, which forces this characteristic X, harmonics. So when waves are only interacting on one line, these harmonics are very hard to get rid of. And that Grisha and Palkovich in his paper with Shaparenko observed these kind of things.
So anyhow, the incompressible is completely
Perhaps
separate.
we can let the speaker conclude because we are. Sorry.
Okay. So yes, I nearly finished. I guess one more thing I wanted to show. I mean, of course, in numerics you can do higher statistics through PDFs, right? So what's interesting, so if you plot velocity PDF, and velocity is gradient of phase, right? You develop, strong intermittent tails with asymptotic and log-log plot V minus 3. So V minus 3 is a signature of a thin vortex filament. So essentially, this is kind of, and that's been seen before in simulations. Carl Baren here too, and also in experiments. I mean, they measure these kind of things. Recent experiments by study vortice connections. But also, if you plot density PDF, right? So initially, when there is no condensate, density must be so this is log lean plot. When there is initially no condensate, you expect Gaussian field, which means for rho it's exponential, because rho is psi squared. So it would be like that. So then in time it develops a maximum, and then it becomes like a Gaussian, but Gaussian with respect to rho variable. So it's like you move in equilibrium. You instead of waves, random Gaussian waves about equilibrium 0, you have it about condensate. But what also you can see here, a enhanced probability of low densities, and these are vortices, because vortices are holes. Vortices are empty spaces in terms of density. So I'll just put my summary slide. So I perhaps two results maybe you should notice that bottleneck crossover picture and non-local picture of alien wave turbulence, both of which are subject of extreme controversy now in the literature. And of course, controversy sprouts both on small scale range of alien waves and bottleneck and large scale. Okay, so and of course, I mean, it all remains more or less idle speculation until we do good numerics. Of course, I mean, that we reach the limit. But then, finally, I want to put the phrase Muriel's that when you compare with numerics, you have to keep in mind that